to start really honing in on your intuition. And so this is where that begins. So anybody get something for these beams that, kind of get a pretty good feel for how these beams will deflect, right? Imagine based on the loading shown, and by the way, unless you're told otherwise, just assume that a load is a gravity load, right? If it's not indicated as something else, right? Assume it's a gravity load. So you can assume with two spans on this beam that the deflected shape would be something like that, right? Things that you need to think about are where the supports are located, what type of support it is, and then also where the load is placed and the direction of the applied load. So what about this one? Free end down, I think that's what folks are saying, right? So free end down, and we know supports, right, are here and here. What about in between these two supports? Bow up, right? Yeah, so it'll do something like that. And then if we switch it up, I'll box myself out there. All right, well, what if we do this? And we have the load on both spans. Assuming the load is constant magnitude, right? We could confidently conclude that the deflected shape would be something like that, right? We exaggerate these quite a bit when we draw them, of course, but this would also be consistent with the deflected shape of the beam just under its own self-weight, because it's a constant uniform load. If we had extra load on one of these spans, right, then we might veer towards one of these more in this situation, okay? So don't worry about that too much right now when you're starting these problems and thinking about how structures will deflect. I want you to mainly focus on thinking about where the supports are and how that will impact the deflected shape, and where the load is applied and in what direction the load is applied. As you get used to this, right, and as you practice this and get more comfortable with your intuition on how structures will respond, you'll develop a sense for also anticipating how different magnitudes of loads will impact that as well. So in your, let's see, we'll get back to that in a moment. I'm gonna put this on the screen now. So for this lecture, right, so this leads me into homework 1. Homework 1 I've already posted on D2L. It's due next Friday by 11:59 p.m. in Gradescope. The first part is the matrix algebra portion, right? And I'm directing you to read part of the appendix in the textbook that covers matrix algebra, and or watch a recorded lecture. So I'm giving you an option. If you'd rather watch the recorded lecture that covers the same stuff, you can do that. I think I also included a set of partial skeleton notes that go along with that lecture. Or if you'd rather just scan or read the text, that's great too. My goal is to just get you up to speed and everyone on the same page regarding these matrix math manipulations, right? And then there's going to be two hand solution problems that I'm making those extra credit this time. In the past, I've always had those as required, but for this semester, I'm going to try this out and see how it goes. So if you want to do those hand solutions for some extra credit right off the bat, get off to a good start, then please do that. Otherwise, if you don't want to, please still read the text or watch the lecture. And then also, everyone should watch these 2 short videos on using Excel that I've linked on D2L. So you'll see a matrix algebra module or folder on D2L that has the links to these videos. They're very short, like less than 5 minutes. And then the third matrix algebra problem is going to be using Excel to solve a system of simultaneous equations. There are some hand calculations that you'll need to provide along with your Excel spreadsheet that I've outlined in the in the homework assignment exactly what you need to include in those hand calculations. It's really just showing what your results are along the way, okay? And then the second part of the homework is getting into that structural engineering intuition and some other stuff, exploration, right? So this is where we get back to the drawing of deflected shapes. There are 3 problems from the textbook that are going to be similar to what we just did at the beginning of class, where you're going to be given a beam with some loads, and you're asked to draw the deflected shape and then also draw the direction of the reactions, all right, reaction forces. So we didn't do that in today's exercise, but that's going to get you to exercise your intuition a little bit more and think about those things. And then, let's see, we'll get to the other stuff in a moment. Oh, all right, yeah, so here's the matrix algebra folder on D2L. You can find, there's some skeleton notes, a link to a recording, and then, oh, right, so if you do watch the lecture, there's a short follow-up because when I recorded this, I made a mistake in one part, and it's something that you'll probably catch if you actually watch it. But there's just a follow-up, a short follow-up video that corrects that mistake. So if you need to watch that, you can. All right, so these deflected shapes, right, they should be hand sketches. Here's a few examples, and this also kind of speaks to some of the homework expectations. So up at the top of the page, first page, right, include your name, course number, the date, and then number each page. After the first page, you don't have to include all that information, just your name and the page number. For each problem, right, use the given find solution format. Just be organized in how you present it. There's a couple different ways you could do that. Don't rewrite the entire problem statement, please. It's not a great use of time or space. Usually a summary or bullet points are sufficient. And it's a good exercise too to read through the problem statement that's given to you and then assimilate the information, boil it down into what's actually critical to include on your homework assignment, right? And then present that information. Any sketches should be your own, all right? So no screenshots of the problem statement sketch. So include a sketch usually in the given portion, and then also as part of your solution as necessary. Now, there is another bullet item in the homework expectations that says start each problem on a fresh page. That's really intended for longer problems, right? A lot of problems that we'll do later in this class are going to take multiple pages to solve. So in those situations, yeah, absolutely start each problem on a fresh page. For something like this, though, you can use your judgment. You don't have to start these really short problems on fresh pages as long as you can complete them reasonably on the same page that you started them on, all right? So that third one, all right, and here I am showing you the direction of the reactions for these guys. Another option, right, if you don't, some students like to just draw a bar underneath the given find, have all that information up top, and then instead of just writing solution, you can just draw that line and then have your solution below that. That's fine too. So the main goal here is that it's easy to follow, right? Organized and very clearly presented. And this isn't just for us on the grading side of things, right? This is also for you as you keep your records and maintain those, right? So you can go back and remember what you did. So the idea is to kind of document your work so that someone who's familiar with the subject but maybe not the specific problem would be able to easily follow what's going on, right? And that also is really good practice for the future when you are working. If you hand your boss a bunch of unorganized calculations, it's going to be tossed right back at you, and you're going to have to redo those. So you want to be very, very clear and organized in how you present things. All right, so the last part of the homework is to do a couple of write-ups, and these are just short responses, right? And nothing too elaborate or lengthy, but I'm just asking you to write a few lines about your favorite structure and include a picture, and then go to that B1M, I mentioned that the other day, and pick a video to watch and then write up a summary. And then also answer a few questions regarding the course and after you've reviewed the syllabus and schedule. All right. Now, these responses are requested to be typed in the homework assignment using a word processor. So for these, you don't have to restate the problem or do a give and find solution format, right? You can just provide a heading or a label or something like favorite structure, go, right? So something like that. In the syllabus, right, I do emphasize that when you are instructed to provide a typed response, that is going to be a big consideration in the grade, right? If you don't, when you submit a handwritten response, you're going to get a significant deduction. Also, though, keep in mind, not all written responses need to be typed, only when it's noted in the homework assignment, all right? So make sure you just read the instructions carefully so that you know if it's required to type it or not. All right, so next week's lectures, we will continue with the presentation format on Monday. And then by Friday, we'll probably start using the skeleton notes format. So all of next week's lecture materials are available on D2L. I know that these PowerPoint slides that I've published are lengthy. And I received some feedback. Let's see, is that better? Okay. I received some feedback last semester that it's best to, when I publish the slides 2 per page, I was doing it 3 per page, but then it has the weird lines that nobody likes. And with 2 per page, I think students found, they could either print them 2 a page if they wanted them larger, or they could print them 2 pages per sheet, or 2 of the PDF pages per page, and then 2 pages per sheet, 2 sides, right? So you can work with it however you want. If you want the hard copies, if you have electronic, it probably doesn't matter too much. So, all right. So now rolling into structural idealization. Start right off with a definition. Structural idealization refers to replacing the structure or load with a simplified representation. All right. And I like to pick the Eiffel Tower as a quick example to introduce this concept because it's very detailed, and as you can see, all these rivets on the Eiffel Tower, over the whole tower, there are 2.5 million of these rivets, right? And there's over 12,000 individual metal pieces that are kept together. All those 2.5 million rivets, each one of them took 4 people to place, right? 1 person to hold it, 1 person to heat it, 1 person to form the head, and then 1 person to lock it into place with a sledgehammer. It took them a little over 2 years to complete this construction. But that four-man method was the quickest, most efficient way to do it at the time. All right, so continuing on with that thought, when do we idealize? We idealize in our drawings, right? We simplify things for the drawings. Of course, the drawings need to be able to communicate every detail, right? But it's still simplified. We also simplify in our structural analysis. Of course, when the Eiffel Tower was designed and built, there were no such thing as finite element models, but some folks have since modeled the Eiffel Tower as well as other historic buildings that are older to assess their performance and compare the results from the modeling to, whatever may have been predicted by the engineers at the time. Or in some cases, these buildings are also now monitored, so you can actually measure the actual behavior of the building and compare it to the finite element model predictions. That's a big part of structural engineering ongoing research. That was a big part of what my PhD research was on, not for the Eiffel Tower, but for other buildings around the world that are newer construction. So I like to show this because what you're looking at right now are the dynamic responses of the Eiffel Tower as modeled by these guys. So again, we're not going to dive into dynamics in this class. I'm just showing you. So you don't need to know this stuff for this class, but it's interesting to point out. And just a basic overview of it, all right, we have different mode shapes of responses for these structures. So you can see them labeled mode 1, 2, and 3. Now these are the positions that the building wants to move into when it moves. And the lowest, there's a frequency associated with each motion. The lowest frequency is the lowest or the first mode shape, right? So that's the most basic one. It's usually a sway mode shape, so just swaying back and forth. And for a structure like this that's symmetric, it would have the exact same frequency in the two orthogonal directions, right? So there would technically be the first two mode shapes would be the same. The way they've labeled it here is a little bit different. So they have the second mode shape at a higher frequency, and this one would have an inflection, right? So if you imagine a straight line going through, it crosses that line at one location, right? So it kind of veers away from the line and then it would cross it. Here, it doesn't actually cross that straight line, it just kind of leans away from it. And then the third mode shape is usually, for most buildings, a torsional mode shape where it's just twisting. Now in reality, when a structure like this responds to wind or an earthquake or some sort of, input, then its response will be a combination of all of its different dynamic mode shapes. And there are more beyond the third mode, all right? So there are higher mode shapes beyond that where there is more inflection points, all right? So imagine just a squiggly line, you can get up to that. But it's a fun analysis, an important analysis. Again, not what we're doing in this class, but something that maybe some of you will get into someday, all right? And one thing I like about this is that we get to see the buildings dance in these finite element model results. At least in one program, SAP 2000, when you get these modal analyses results, you can hit animate and it'll show the building dancing, and it plays some music that is synced to the frequency of the mode shape. So it's kind of fun. All right, so going back to our structures and back to statics and static things. We've got loads and structural components, connections, and supports. We idealize all of those things. So if you can just see how this beam is supported by these concrete block walls, and that beam is supporting these different joists that are framing into it. So in reality, those points or those surfaces of contact are an area, right? So those loads at the contact surface are distributed over the width of these members. But this is a lot more complicated to analyze than this, right? So we simplify all of those points of contact to a discrete location, and then we just have point loads to deal with. This is also conservative, so it helps us with our analysis, and then if we need to, at the end of the day, we can go back and just verify, check some things and verify that everything's okay with the true condition. And if we did that, we would basically just run our whole analysis using the point loads and then identify maybe the worst case location and then investigate that one more closely, right? So we also idealize trusses big time, right? So a lot of times those truss connections have significant geometry, but in our analysis we idealize those as just simple points that occur at the line of intersection between the members, right? All right, so how do we idealize these items? Well, I already alluded to this, right? We've got points, lines, and areas. All right, this is how we simplify structures. And here I've got the different units associated with the loadings, and then examples of different types of structural elements for each one. And we're going to go through this a little bit more, one by one for different elements. But one thing I'd like to point out is that point loads do not have to be applied at points or joints, right? Point loads can be applied on line elements and on area elements. Similar with line loads. They don't have to be applied on a line element. They can be applied on a surface area element. But we would not apply a line load to just a joint, all right? A joint might be included in our line load between, right, with the element in between it, but you get the idea. Okay, so here's an example taken from finite element software program called Visual Analysis, which is the software program that you will be using in this class later on. So you can see some more information about that in the syllabus, and I'll provide you more information with that as we get closer. But you will be working with this program in this class. Now this is showing just a simple three-dimensional model of a single-story, single-bay frame. And on the right side, you can see it with the lines that we use to idealize. You can see the extruded geometry. So that's often called an extruded view, where it shows you the relative shapes and sizes of the individual elements that you have selected. So we can see that the beams are I-beams, right? So they have a long web and then some flanges at the top and bottom. And then the columns look like they are some kind of tube section. So that view is nice to have access to, because if you turn it on, you can verify that these sections are oriented the way that you want them to be, right? Because as you remember from mechanics of materials, a lot of cross-sectional shapes have a strong axis and a weak axis of bending, right? So we want to make sure that our beams are oriented so that it's in strong axis bending. And this is one way to do that. And usually they are by default, but it's always a good idea to check. And then this just shows the deflected shape of this frame under its own weight. All right, so now I'm going to talk a little bit about structural materials. So wood and masonry, of course, are probably the oldest structural materials that have been used for many, many thousands of years, right? In the old days, they looked a little bit different than what you see here, but a lot of the older masonry structures are unreinforced. All right, so today we would not design any new construction as unreinforced for structural purposes. Does anybody see this story from earlier this year? You saw that study? Yeah, this is pretty interesting. There was in January they published this article. They figured out how the Roman cement is still around and still intact, and it has more to do with how they mixed it rather than what exactly was in it. They did use volcanic ash, and they used hot mixing. So with the hot mixing, they created some compounds that could only be created or only be formed at high temperatures. And then those compounds, so what would happen then is if the material cracks, water will enter into the crack and react with these lime clasts and to form like a calcium concentrated solution. And then that would recrystallize into calcium carbonate and fill the crack and also strengthen the material. And all of that would happen instantaneously, all at once. And so essentially it would prevent the cracks from spreading as they form. All right, so it's like they created their own self-healing concrete. It's a really interesting story. I'll try to find the link to this and post it on D2L for anyone who's interested, but it's pretty cool. I just wanted to throw it in here. All right, so back though, right, unreinforced masonry buildings, really, really poor performance in seismic design, right, in earthquakes. So we don't want to do that for new construction. All right, so all of our new construction for masonry should be reinforced if it's for structural purposes. All right, and then we of course have steel and concrete, reinforced, of course, concrete. And so these four, wood, reinforced masonry, steel, and reinforced concrete, these are the four major players in structural engineering, right? And each one of those has its own industry organization to represent it. This is a great example of propaganda in structural engineering. So if you thought that by choosing an engineering major you could avoid drama and politics, I've got news for you. It's everywhere, right? So this is an ad that was released several years ago by AISC, the American Institute of Steel Construction. So of course they don't want people to build with wood, right? Now I think they've changed their tune a little bit, and they're more promoting hybrid structures, so wood and steel, wood and concrete. But this was, I think, back in like 2016, 2017 when they started putting those ads out. And the reality is there have been many advances in wood design, right? So of course we all know wood burns, right? So this is put out by the Mass Timber Coalition, and there have been significant advances in mass timber, which is a specific way to basically put together a wood element, all right, a wood cross-section. And so what they're saying here is that in fire, an outer layer of char will form on the wood element, and that charred outer layer will then act as protective insulation to the inner core that would remain unheated. And so in that way, it kind of forms its own fire protection in the event of a fire, and then it doesn't actually burn down. So it's really interesting, how they're proceeding with that, and it's starting to gain traction. Wood is becoming more and more prevalent in larger construction projects. Steel does need to be fireproofed itself, right? So you've seen steel members with this ugly spray coating on it. That's fireproofing. It's required for structural members that are part of the main structural system. And if you don't see that ugly spray coating, then it's probably painted with a more expensive material that looks nicer, but again, it's more expensive. So sometimes it'll be painted that satisfies the requirement for fireproofing. Masonry and concrete, those materials are inherently fire resistant, so they don't need any additional steps for fireproofing. This is the world's first iron bridge. It was completed in 1779 in England somewhere, I forget exactly where. And this I put in there because, again, first iron bridge, it is said to mark the beginning of the Industrial Revolution. Other structural materials that you may see in certain applications, we've got aluminum, composites, even bamboo. All right, so these materials have different limits, so they can't necessarily do the same things that steel, concrete, and the others can do, but they have their place. A few years back, some students came up with a bamboo fiber composite material, and now they have their own company that produces this material. And it's not used for structural purposes, though. I think it's just used for flooring, like non-structural flooring and stuff like that, but still pretty cool. All right, so now we're going to go into these structural components, and I know you all know what these are. We're just organizing them into context that we are going to be focusing on in this class. So first up, we're going to talk about a bunch of different line members, right? And so on the left side of these slides, I've got the idealization summary, and then on the right side, what internal forces we design for with each member. So first up, we have an axial bar. Now this is one type of two-force element. A two-force member or two-force element is specifically a member that is configured so that the internal forces are all on the same line of action. Now this is one of three two-force elements that we're going to introduce today. The internal forces of an axial bar could be tension or compression, right? So you would design this to be able to resist both. A cable or tie is a two-force member that can only take tension, right? And then a strut is a two-force member that only takes compression. Now we can tell the difference between cables or ties and struts by the geometry, right, the cross section. So here's an assembly with a bunch of different members framing into this point here. And just by looking at it, you can tell which ones are the ties. I've marked them with a T, and which ones are the struts. I've marked them with a C for compression. Now I see that's a little bit confusing because I also said cable and tie. Anyway, okay, so C for compression, T for tension. So the tension-only members, right? The most efficient way to resist tension is just with a solid cross-section. So this is how much cross-sectional area is required to resist those tension forces. Let's say that the compression forces in this assembly are about the same in magnitude as the tension forces. If you apply compression to one of those tensile members, it's just going to buckle, right? You've got the wet noodle thing going on. And then, so in order to avoid that, we don't want it to buckle, we can take that same amount of cross-sectional material area and spread it out. And then that will stiffen the cross-sectional area and it won't buckle. So these compression struts are hollow inside, right? And all of the material is as far away from the center as it needs to be. All right, for beams, these again are line elements that support transverse loads. The internal forces that are generated by those transverse loads are shear and moment, right? You're familiar with this. Now, beams are a general term that include girders and joists, which are terms that we'll talk about more next week. Purlins and rafters, which are specific to roofs. Transverse load is specifically a load that is applied perpendicular to the length of the member, right? So just a little vocab there. All right, moving on to column. All right, vertical line element that carries primarily axial compression. Columns may also need to be engaged in tension, so we need to think about that in our column designs. But generally, they have significant compression for the most part. All right, now a beam column is a vertical line element that can support axial, moment, shear, right? Or those are the internal forces that we could expect to see. Primarily axial or moment. And then there would be some shear if there are also some transverse loads applied. An arch would be idealized as a curved line element, and an arch would support vertical point or line loads. So notice I didn't say transverse for the arch. If we had transverse loads on the arch, then we'd have, right, it would be following the shape of the arch, then it would behave more as a curved beam. You would have shear and moment forces inside that arch. But for our arch action, right, with just vertical loads on it, we would just have primarily axial compression. Here are some pretty pictures of arches around the world, representing different materials and different eras of design, right? Now this is not an arch. This is more of that curved beam situation. But I like this image, and I always like to include it in here because it's a cool building. Is anybody familiar with this building? Recognize it? No, but you're on the right side of the country. It's in Tacoma. So it is the LeMay Auto Museum, I think. That's what it's called. Yeah, it's an auto museum in Tacoma, Washington. So pretty cool structure. All right, so now we're on to flat plates. So flat plates, of course, will be represented by area elements instead of line elements. And there's a few different functions, I guess, is how I've divided these slides up. So first up, we're thinking about out-of-plane behavior of a flat plate. The out-of-plane direction would be the weakest for a flat plate, right? So you imagine just, it's easy to bend this out of plane, right? That's what I'm doing right here. And so that's what the OOP stands for, out of plane. Now this could represent a floor, which we also call diaphragm in structural engineering terms, right? A floor or diaphragm resisting vertical loads or a wall resisting lateral loads. So we always have to think about those elements with respect to out-of-plane behaviors. But we also need to think about those elements with respect to in-plane behaviors. All right, so it's a lot harder for me to bend this folder in plane. I can't do it. But that's what we need to design these diaphragms for, all right? So a diaphragm is an element that specifically transfers lateral forces to vertical elements, right? It's a horizontal plate. Generally speaking, all floors in a building are used as diaphragms. And the internal forces that we're concerned with would be tension or compression in the plane. For walls, if we have a wall that is resisting in-plane forces, then we call that a shear wall. All right, so this is a wall that's designed to resist lateral forces that are applied to the building. And that's something we're going to talk about more next week. Sometimes shear walls are also responsible for resisting vertical loads or gravity loads. But generally speaking, shear is a significant function of these walls. All right, so here's an example of flat plate construction. This is a pretty significant span of this reinforced concrete floor to not be vertically supported, right? And they can achieve this through post-tensioning. So this was a milestone really for high-rise structures, allowing for these vast, views without columns in the way. But it's pretty cool. So they call it flat plate construction. All right, so then last but not least, we have shells or thin curved plates. So here we could have vertical or transverse point, line, or area loads, right? And then the internal forces that these would be designed to would be tension or compression in plane. So a good example of this is the field house right here on campus. I've got a few images here of the field house under construction. These I just found on the MSU website somewhere. So you can see them putting the frame in place. And I think at the time that this was built, it held some record for like the largest structure of its kind. So pretty cool. I think it was built in the 50s. All right, so any questions so far? And we're kind of quickly going through a lot of material. Yes?
Why do you need the fireproof steel?
Well, it's a code requirement, right? And we don't want that steel, if it gets to a certain temperature, then it starts to degrade in its strength, right? Yeah. So we want to protect it against that. Okay. Any other questions? Okay. So now we'll talk about structural supports and connections. There are two different ways to think about these structural supports and connections. One is in terms of motion, and the other is in terms of forces. So first, I'm going to explain them in terms of motion. So a support is specifically something that prevents a member from moving in at least one direction, either translation or rotation, right? Usually supports involve connections, most of the time. A connection is specifically an attachment between two or more members so that they all have to move together in at least one way. So the connection itself is free to move though, unless there is an external support at that location. In terms of forces, support can be described as an element, structure, or foundation structure that provides external reaction force or moment in at least one direction. Connection is a joint between two or more structural members that is capable of transferring force and or moment across that connection. However, it does not provide any external reactions, right? Again, unless it's a connection at a support. However, there is a caveat here. So connections are often treated as supports for the members involved if we isolate that member for analysis, okay? So we'll see that in an example next week. these are the three major categories of supports, all right? Now, in reality, every support or every connection falls somewhere in between its idealized behaviors of these three options, right? So the idealization is summarized here, right? Frictionless surface, frictionless pin, or complete resistance to everything. In terms of motion, all right, we assume that there's no resistance or rotation or translation, or excuse me, no resistance to rotation or translation parallel to the surface, right? So we assume that in the roller support condition, there's only resistance to motion in the vertical direction, right, perpendicular to the surface. And that goes for upwards and downwards, which is always a little bit confusing, I find, as a student, because we idealize it as this circle. It looks like the beam can just lift right off of it. And there are situations where that support exists, right? So that is possible. But generally speaking, for structural engineering applications, our roller supports are configured so that it prevents vertical and downward, or vertical upward and downward motion, right? So assume that that is the case unless noted otherwise. All right, so you can read the rest of them. I don't need to read that out loud. In terms of forces, you've got the assumptions shown here. Now again, in reality, supports are usually somewhere in between, but these are how we idealize them in our analysis. Sometimes we need to use springs to represent supports. So a spring, you can have a linear spring like this one, or a rotational spring like that one. So these can allow movement and also transfer force. An example would be like soft soils. We're not going to deal with spring supports in this class, but it's important to be aware that that's a possibility. All right, so here's an example of some of those roller connections that prevent motion, right? For the horizontal roller on the left, you can see how that motion is prevented both up and down. And then the vertical roller shown here would prevent motion side to side, right? So this is a typical connection for attaching the edge of the concrete slab on metal deck to the metal stud wall. And the purpose of that connection is to prevent that slab from drifting away from the wall. That wall is not supporting the slab, right? The beam is supporting the slab, and then that beam would be supported by columns or maybe a different wall or something like that. So that slab will deflect with the beam, and we want it to be able to do that, which is why we allow for that vertical deflection with these long slots. All right, so here are a few examples of shear connections, all right? And then when we're dealing with steel connections, all right, they have varying degrees of joint rigidity. So here you're seeing an example of a full moment resisting joint. There's more ways to configure this, but this is one example, right? You have a bolted angle attaching the web of this beam to the column of this, the flange of this column. You have welded angles connecting the flanges of the two elements. And then you have continuity plates that extend the behavior of that top and bottom flange of the beam. So that brings that full moment transfer all the way through the joint. If you remove those stiffener plates and welded angles, then you're just left with a pin connection. So here you see the spectrum of different different types of steel connections, from ideal pin to ideal rigid. And then here's an example of a joint that includes a full moment connection on these two sides, and then a pin connection with this beam bringing in to the face of that column. So you can see the difference, right? A lot more is involved in that moment connection. All right. So for reinforced concrete, we assume that the connections can transfer moment if the steel reinforcement is continuous through the joint. So we've got vertical bars, all right, that continue past all the way through the joint. You can see that here and in that example as well. And then here, the beam ends at this point. So where the beam ends, that horizontal reinforcement continues as far as it can into the column and then is curved downward. If the beam continues, then of course the horizontal reinforcement will just pass straight through. But we want it to be continuous, which means we don't want to splice that reinforcement in the connection. We always avoid doing that. So we make sure that the splices, which is where we would overlap different pieces of steel, those splices would occur typically for beams around the third points or midpoints of the span, and for columns usually around the quarter points or third points. So we just want to make sure that they're away from the connection, because you can imagine how congested that would be if we were splicing things in there, but also it's an integrity issue. So it's a code requirement to avoid that. All right, for reinforced masonry, that's similar to concrete. The moment resistance depends on the continuity of the steel reinforcement. So there are code requirements to make sure that that's achieved. And for wood members, we typically just assume that connections are pinned, right? It's very difficult to achieve moment transfer with wood connections. All right, so this is a good place to stop for today. So I think we're close to the end of this lecture, but it really blends into the next couple lectures anyway. So any questions? No? Okay. All right, well, thank you all for your attention. I will see you on Monday, and I hope you have a great weekend.